Now we're going to discuss logarithmic growth. The function we'll study in this section is called a logarithm. Logarithms allow us to convert numbers so that we may compare large and small numbers alike. If b to the x equals a, then the logarithm with the base b of a is x. So what we can say is this: if b to the x equals a, that is interchangeable with log base b of a equals x. We can switch things back and forth. Sometimes it helps us to have everything in terms of a log, and sometimes it helps us to have it in terms of exponent. So example 1 asks us to write each of the following in its equivalent exponential form. So 2 equals log base 4 of x. You start with the base, and then the equals number, this one, so 4 to the 2, and then the of equals x. 4 equals log base b of 81 would be b to the 4th equals 81. And it's not asking us to do any solving or anything here. Just rewrite them. And x equals log base 5 of 125 would be 5 to the x equals 125. Then we can go the opposite direction. 8 to the x equals x. Oh, I think one of those x's was supposed to be a 3, so I changed that. Okay, so 8 to the 3 equals x would be log with a base 8 of x equals 3. X to the 4th equals 16 would be log base x of 16 equals 4. And then the last one, 6 to the x equals 216 would be log base 6 of 216 equals x. Whenever I'm working these, I always make sure that I have this in front of me. A common logarithm is a logarithm with a base of 10. We usually express this function as just log of x. Instead of putting the 10 in the base, we leave the 10 out because it's a common logarithm. It's so common that we don't worry about putting the 10 down there every time. So if you ever see just log of x, then you know that means log base 10 of x. Past research tells us that our bodies grow at a given rate based on our DNA and the environmental factors in which we grow up. Assume that a baby girl is born and is 22 inches long. If we consider that the baby will grow at a rate proportional to her body size until adulthood, then the percentage of her adult height attained can be modeled by this function. F of x equals 22 plus 55 times the log of x plus 1, where f of x is the percent and x is her age. What percent of the girl's adult height is attained by age 12? So let me write down our function again. And all we need to do is plug in 12 for x. I'll go ahead and add 12 and 1 down here. And then we need to go by order of operations. Do not add this first. You will end up with a wrong answer. Order of operations says we need to do multiplication first, but we need to take care of the log before we can multiply. So you'll do the log of 13, then multiply by 55, and then add 22. And we get about 83.267. So a girl reaches about 83% of her adult height at 12 years old. The Richter scale is used to measure the intensity of an earthquake. The actual model is a little more complex, but it can be simplified to this equation. R equals log of I over I naught. R is the magnitude on the Richter scale of the earthquake. I naught is the intensity of an earthquake that is barely felt, a zero-level earthquake. And I is the intensity of the earthquake measured relative to a reference value. Every increase of 1 in the Richter scale means the magnitude of the earthquake is 10 times greater. What is the magnitude of an earthquake that is 1,000 times stronger than a zero-level earthquake? Okay, so a zero-level earthquake's magnitude is 1. That's just what we use. It's because that is the original zero level 1. And this earthquake is 1,000 times greater. So we'll plug in that for I. So basically we've just got to put in our calculator log of 1,000. We get 3. So the magnitude of an earthquake 1,000 times stronger than a zero level is 3. Recall from the beginning of the section that the earthquake created a huge tsunami, it must have been something else, off the coast of Sumatra in October 2010. It was a magnitude of 7.7. If I naught is 1, what is the intensity level of the Sumerian earthquake? So remember, we've got R equals log of I over I naught. This time we've got the magnitude, it's 7.7. And I naught is just 1. So we've got equals log of I. We can't solve this for I in this form. So what we do is we use the little change-a-root thing, where we change it to an exponent. We would take the base, which is 10, raise it to the 7.7, and that will give us the intensity. And 10 to the 7.7 is 50,118,723.36. Seems quite intense to me. An earthquake that hit Chile in 1960 was estimated to have been about 9.5 on the Richter scale. That's the strongest earthquake ever recorded. Find the intensity of this earthquake if I is 1. So we'll just do the same thing we did on the previous example. So 10 to the 9.5 will give us I. That's 3,162,277,660. Would not want to have been there. The sound intensity level measured in decibels and given by this formula, where decibel is 10 times the log of I over I naught, measures the intensity of sound I based on the reference value I naught. The value of I naught is the threshold of hearing at 1 kilohertz, so we consider this value to be equal to 1. If the decibel level of a certain sound is 115 decibels, what is the level of intensity of this sound? So we'll plug in 115 for the decibels. And I naught is just 1 again, so we've got log of I. Now before we switch things around, we need to divide both sides by 10 to get log of I by itself. So we've got 11.5 equals log of I. And so now we can say 10 to the 11.5 is equal to the intensity. That's 316,227,766,017. So this sound is even more intense than an earthquake. And last, the natural logarithm is a logarithm with a base of e, where e is an irrational constant approximately equal to 2.718281828 and going on. We treat e very similar to pi because e is just a number, just like pi is a number. The natural logarithm is generally written as ln of x. And ln of x means log base e of x. We just write it ln because it's another common occurrence, and so it's just easier to write it that way. Also, you could know, it's helpful to know that the natural log of x is equal to the log base 10 of x over the log base e, or base 10 of e. Human memory capacity, the percentage of information in the average person can recall after a certain period of months have passed, can be modeled by the function f of t is equal to 85 minus 15 times the natural log of t plus 1. Where t is the number of months that have gone by after being presented the information, and f of t is the percent of information retained after t months. What percentage of learned material was retained 6 months after being presented with the information? So we're just going to use our formula, and we plug in 6 for t. We'll go ahead and add that 6 plus 1 to get 7. And then keep in mind again, do not subtract. You got to take the natural log of 7, then multiply by 15 and subtract that from 85. You get 55.8113, or approximately 56% of material learned is remembered after 6 months. Yeah. Okay. Well, that concludes this section.